Hello students, and welcome back. We're into Module 14. Now, before we really get into the meat of Module 14, I thought I'd play a little bit of a game that I usually do inside the classroom. So, imagine I've got a deck of cards, 52 cards. This is on a website called random.org where you can actually have kind of random numbers, and in this case, random card shuffles, without having me kind of hold up cards. What we're going to do in the classroom, what I usually do is I'll play a little bit of a game, and people can line up in the room if they'd like, and I usually pass out candy or cookies or something like that. And so if you come to the front, I'll open up a deck of cards. I'll unwrap the plastic, open up the deck, shuffle it, and then if they draw a red card, I give them a cookie or candy. If they draw a black card, then I'm sorry, you get to go sit down, and you had a chance. So that's the idea, the basis for this. So here's kind of what we're going to do. We're going to play this a couple times. And so here's my one card. Okay, so I'm going to click again. We're going to draw a card. Here we go. We draw a card, and it is the 9 of spades. So if that was you, I'm sorry. Go ahead and have a seat. You did not get a cookie this time. That's all right. We'll draw again. I get the 7 of clubs. Again, the next student up would be asked to go sit down. Sorry. Let's see here. What do we get next? We'll draw again. Ace of clubs. So again, I'm very sorry. And if you were asking, and it's a good point in time to ask here, is the way that we do it is you put your card back in the deck and I kind of reshuffle. So that's exactly what's happening here. So it's very likely that you might get a card more than once. It's possible. After you keep drawing long enough, the odds go up quite a bit. So let's try again here. Okay, Jack of clubs. Ugh. Oh, okay, I'm really sorry. I really want to give away these cookies. I made their homemade cookies. They're fantastic. Let's try maybe one more time here. 2 of spades, and I know that the next student up is screaming, "Come on, give me a chance! I want a chance! I need a cookie! I haven't eaten today." Okay, we'll try one more. And Jack of clubs. All right. Well, I'm gonna pause there because this brief example gives us a chance to really think about what's going on in statistics. So at this point in time, take a standard deck of playing cards. There's 52 cards. 26 are red and 26 are black in a standard deck of cards. Now, perhaps at some point in time as you were watching that, there was a part of you that was saying, wait a minute, that something doesn't feel right. And depending on where you are in your understanding of mathematics, you might begin to say, that feels weird. That feels strange. That's like flipping a coin and somebody just keeps getting heads over and over again. If there's 26 red and 26 black, that's a 50% chance of the time I should get a red card, and so far we haven't seen a single red card. Well, out of all those options that we had, let's just say maybe we had 6 in a row, 7 in a row that were black, you start to really begin saying then, well, wait a minute, it's possible that someone could get 6 black cards in a row. I mean, if you think about the deck of cards, it's certainly possible that someone could draw randomly, reshuffle, draw randomly, reshuffle, and get 6 or 7 black cards in a row. As a matter of fact, I mean, they could keep going. They could get 10 black cards in a row. But what we then begin thinking about is, now this is where probability comes into play. We start asking, well, what would be kind of the chances that would happen randomly? And so as you think about it, if each card has a 50% chance of happening, and then you kind of say to yourself, wait a minute, 50%, 50%, 50%. Let's jump over to Desmos and we'll see what we can find out here. I'll use the scientific calculator in Desmos. And let's just try that. 50% times 50%. So for us to get a black card 2 times in a row, that would happen about 25% of the time. And that kind of makes sense if you picture it, right? You could get a red, then a red, you could get a red, then a black, you could get a black, then a red, or you could get a black, then a black. So it's kind of 4 outcomes. They're all equally likely, and this one's going to happen 25% of the time. But if I draw 3 black cards in a row, now we're starting to get into something that's a little bit more rare. So now it says 0.125. So that's about 12.5% of the time. Okay, 12.5% of the time. That's great. It's still, it's not horribly rare. And I'm going to switch my notation. Instead of multiplying over and over again, I'm going to put in some parentheses. And then I'm going to raise it to a power. And that's using this little button right here, or pressing Shift 6. And then I'm going to say, let's do this 7 times in a row. So my chances of getting a black card, put it in, shuffle, redo it, put it in, shuffle, redo, 7 times in a row, it's not 1 in 10, it's not 1 in 100, it looks like it's about 7 times, maybe close to 8 times in 1,000. So this is where we come back as mathematicians and we bring back the probability and say, now you have a case. Your gut feeling was kind of telling you something weird is happening here. Now, even though it's possible that this could have happened, you might begin to say, I have pretty convincing evidence that something strange was happening with that deck of cards. Maybe you think I chose a deck of cards that isn't half red and half black. Now, you'll never really know the answer to that, but you will be able to have convincing evidence. Okay. So when you take a look back at Unit 14, which is a little bit shorter unit, remember the goal here. We are going to be taking our population, taking a sample, taking a look at that sample and analyzing it, and then using probability to link back to make a statement about the population. Now, I did that with playing cards, and I'll probably reference that example a few more times. I think it's a pretty good example. And for most people, 7 times in a row is, they would absolutely say, that's highly unlikely. That's very, very strange. But most people, it turns out, get there right around 4 times in a row, or possibly 5 times. Something that happens like that. Maybe you flip a coin and you get 3 heads in a row and you're like, okay, that's not too bad. You get 4 heads in a row and all of a sudden a little warning bell goes off inside your mind. And so this is a pretty natural place. So this is right around, if you notice, these numbers are both pretty close to about 5% of the time. Which, if you put 5% into a fraction here, it's 1 in 20. So that means that we're okay saying to someone that I don't believe you if the event that we witnessed happens 1 out of 20 times or less. 5% of the time or less. And we're okay with that because we know we can never be 100% convinced. So what we have is we have convincing evidence, but we don't have necessarily this idea of proof, like a math class, is your answer true or false? Those are the only answers. And here, we just have convincing evidence. Let's see how this plays out in one more example before I wrap up this short video. So one of the examples shown here is the role of random chance. Now, this was a case of cheating back in 1984, University in Florida. A student was kind of caught by the teacher. Looked like they were copying answers from another student, and it went to the university's court in that case. So each university actually has this kind of student conduct court, and it went to trial. And the evidence was that 16 questions were missed by both student A and student C. Those are the ones they got wrong. And 13 of those wrong answers were the same. And so now you have to make an argument based on probability. And the person making that argument was saying, aha, there's no way that this could have happened by random chance. Or to say instead, maybe it's highly unlikely that this would happen by sheer guessing. So what they did is they put together this little table. Here's the 16 questions missed by both students. Now again, here's student A's wrong answers, and here's student C's wrong answers, and you can see the green check marks match up with showing that 13 of the 16 actually match. So then what they did is they went and said, well, let's just randomly select answers for a couple other students and pretend that we had 3 other students here and that they were just randomly guessing answers instead of looking at student A. Now, what we can see is at times those random answers are going to match up. But how often is that occurring? So the random answer number 1, you can see there's 1, 2, 3, 4, 5, 6 that matched with student A. They pulled random numbers again. Here's now 3 of them that match with student A. And you pulled them again, and here's 5 that match with student A. So we've got a 3, a 5, and a 6. Nothing close to 13 that match if we're doing this randomly. Okay? You could even start creating a distribution. So continue pulling random numbers and seeing how many of them match. And that's what they kind of did down here. They ran 1,025 random answer sets, and how often did those match up? 20% of the time, 40% of the time? And what you can see is, here's the blue line of where the student was kind of said, well, we think you're cheating. It's about 81% of the time. And out of 1,025 random answer sets, you can come to the conclusion, I feel very confident that that student was looking at someone else's paper. And so again, this is where we use inference. We are not guaranteed 100% sure, but we have such convincing evidence that we believe that this is the case. Okay? I think it's fun to read on about that example. The student did appeal the case and came back to talk about comparing every student's paper, and they counted the number of matches. How many times did it actually match, whether it was right or wrong? And so what you ended up with here is, once again, you ended up with such a high probability. It wouldn't be unheard of. If you look at this distribution, it would be okay to think between 40 and 60% would match. And that's where kind of a typical number would be with this distribution. However, the student had 80% of the answers match. So 81% of the wrong answers matched, but 80% of all answers matched. And so if you take a look at that, that's way outside of where we would expect to see everything coming together. And you'll notice there is one dot way up here. That means someone got 100% of their answers to match student A. If you're curious, that is student A. And so, when you take a test, every one of your answers does match your answers. So, in any case, that's the point of this next section we're coming into. We're really going to make a turn from analyzing data to starting to analyze it with the intent to take it back to that population. So I'm super excited about this. I hope you are too, and I look forward to the next few modules. We'll hit 15 and continue going on. Also, one other piece I want to point out, we are moving into a place where instead of having 2 modules for every due date, that will become pretty rare. That should only happen if we have small modules. We'll try to move down to 1 module per due date as we continue going forward. So I'm pretty excited about that for the online class, and please let me know if you have any questions. All right, off you go.